Good evening, everyone. My name is Ben Walker. I'm the head of School for Physics. It's fantastic to see a good crowd. Whereas today is a special day. Today we have Steve Sherwood, who's going to talk about climate change. And that is fantastic in terms of physics because we have a really important topic of our time that does require like the real skill set, complete skill set of physicists. Steve is in the Center for Climate Change Research. He's also has a co-appointment in physics. It's another example of how we work very closely together and really try to make a contribution to this big problem. I'll leave all the comments about the US election to Steve. Now to really verbally educate the world. We're going to have a talk for about 45 minutes and Q&A afterwards. Stephen is not only a esteemed researcher here at UNSW, he is also an ARC Laureate Fellow, which is the most esteemed highest level ARC professorial level fellowship that exists in Australia. Steve, please.
Thank you. Thank you very much. Can people hear? Wait till. I'm going to talk about climate change and try to say a little bit about the physics of the problem. And stop me whenever you want. I always prefer to answer questions rather than blab away on what I think people might want to know. Excuse me. So I just thought I'd start out with this quote from a book that my son was reading recently, The Hitchhiker's Guide to the Galaxy. This is all about sustainability, okay? There's a sustainability problem on this planet where so many people visit the planet every year that they're worried about the planet losing mass. And so they recommend that you get a receipt when you go to the lavatory, otherwise they'll take it out of you when you leave. All right, so we don't have that many visitors to planet Earth, although I'm starting to wonder. But what we do have is an atmosphere that, while it can get rid of carbon dioxide, it's extremely inefficient and slow at doing so. So if you add carbon dioxide to our atmosphere, it stays there for a very long time. And many of you have probably seen this curve before. This is the series of measurements that have been made at Mauna Loa since the International Geophysical Year 1958, showing the very smooth rise of carbon dioxide in our atmosphere, together with a seasonal cycle, which is because there's a lot of plants in the northern hemisphere and they take up CO2 in the spring and they release it in the autumn. And in the southern hemisphere, that effect is smaller. But apart from that, there's this rise. And there's a report coming out tomorrow, I think, saying that for the second year in a row, global humanity has, there's a slowdown in the rate of production of CO2 by humanity that has continued for another year. So that's good, but that's the second derivative of human production, which means it's the third derivative of concentration in the atmosphere. So it's not exactly the same as saying that we're actually bringing this down. And you can see that, in fact, in the very last year here, there was a record-breaking increase in the actual amount of CO2 in the atmosphere. That's, I think, mainly because there happened to be a larger than usual exodus of CO2 from plants and stuff. But this is what's going on in our atmosphere. And if you're just curious what was happening before the International Geophysical Year, there's an estimate from CO2 in ice cores that you can get. So basically not much happening until the Industrial Revolution. The amount of CO2 that we put into the air is really pretty stunning. So here's somebody's artist rendition at Carbon Visuals of the volume occupied by 1 day's emissions in Australia, okay, if you put it in the Sydney CBD. So, it's not surprising when you see that if you add it up over all the world, it is enough to cause that rise that we saw. Now, one of the things that I hear skeptics say once in a while is, CO2 is only 400 parts per million, 0.04% of the atmosphere, so how can it do anything? Okay, it sounds like it's negligible. So actually, somebody sent me a document the other day, and I skimmed through it, and it had an interesting calculation in it, which I hadn't thought of doing before. So I'm going to ask you guys if you can guess the answer. It's true, this is a very small number. But the question I want to ask is, if I imagine a geometric ray going straight up from the surface through the atmosphere. How many carbon dioxide molecules do you think it would hit? Okay, and you need to know, I'm imagining that hitting a carbon dioxide molecule means that you somehow intersect that sphere, okay, where this is roughly 1 angstrom. Okay, 1.1 angstroms, I believe, is the interatomic distance between the carbon atom and the 2 oxygen atoms in a CO2, COO. So knowing that this is the percentage, who wants to make a guess? How many of these molecules a ray would intersect going through the atmosphere? It's going all the way through the atmosphere, up into space. Oh, no, 0. Okay, so the ray has to hit somewhere between this radius of the center of mass, the center of the carbon atom, in order to hit the molecule. 0? Okay, any other guesses? Can't be 0. Well, it could be a fraction of a.
Well, if you think about the pressure of the surface of the atmosphere, you can work out the volume.
Right. So I did this calculation. I'm just wondering if anybody wants to guess what it is.
And remember that there's 10 to the 18 molecules in a mole.
There's a lot of molecules in a.
My guess would be 10 to the 24 or something.
That's interesting. Okay, we're only off by 24 orders of magnitude. You guys must be astrophysicists. Anybody else want to guess? No, somebody had your hand up here.
A lot.
Oh, a lot. All right. So I get 1.5 million, okay, when I do this calculation. So hopefully I didn't make a mistake. That's a lot. So even if the probability of absorption or scattering per collision is extremely small, there's going to be no way for a photon to go from the surface all the way through the atmosphere and get to outer space. So we would expect a priori that carbon dioxide, even at this concentration, would be pretty good at absorbing infrared light. And when you look at a spectrum looking down from space, you see something like this. This is actually a model calculation, but I'll say more about that in a minute. But this is what the spectrum looks like. And I don't know if you guys know about blackbody radiation, but all things in the world emit radiation at in a distribution that depends on their temperature, if they're opaque. And that's shown for the surface temperature of the Earth at the location where this spectrum was simulated or obtained, in the red curve. So the distance between the red curve and what's shown here is what we could call the greenhouse effect of the atmosphere. It's the reduction in the amount of energy that leaves the planet, and because of the absorption. And you can see here in the carbon dioxide part of the spectrum, there's a pretty whopping loss of radiation. So there's a lot less radiation going to space. And this kind of thing can be observed by satellites. So we can see this. We don't have to theorize that CO2 has this effect. And we can also see other things here. We can see ozone exerts a greenhouse effect. We can measure how big it is by roughly by the area of that. Methane is over here, blending in with water vapor, and there's also water vapor over there. Okay. Somebody told me that quantum physics is coming up in lots of your talks. So I'll just say that this wavelength here corresponds to a frequency of light that matches the vibration frequency of this molecule. So if the molecule is vibrating like this, it absorbs photons that have a frequency that matches this frequency. Okay, so they're doing this, and that's why they absorb a lot. And that's actually a double. There's 2 quantum numbers associated with that because it can go like this or this. It's an axisymmetric molecule. So this is a very good absorbing band. There's other smaller bands that you don't see very much on here, but that's the main one. So quantum physics is raising the temperature of the planet, unfortunately. Okay, so there's the greenhouse effect, as I said. Now, I had an interesting exchange with a senator from Queensland, Richard Pearson. Anybody ever heard of him? Is he here? Okay. Big surprise he's not here. All right. He decided to do an experiment with 2 boxes. He filled one with CO2, and he didn't fill the other one. And he set them out in the sun and found that they came to the same temperature. And then introduced a law in Parliament that we should banish climate change research and rule it out as anything the government should do on the basis that he had just proved that it wasn't correct. Okay, and this is serious. This is no joke. And then Graham Reedfern wrote a somewhat snarky comment about this. And there's a big quote by me later on because he asked me to evaluate this. One problem is this is the opening paragraph from his blog post on this. He talks about the backscattered radiated transfer of infrared heat. That's already a sign he doesn't know what he's talking about because the greenhouse effect has nothing to do with scattering. It has to do entirely with absorption and emission. But I think fair enough. Somebody's doing an experiment. He's trying to test something. But there's a reason why this doesn't work. Okay? There's a reason why you don't get a greenhouse effect in a box. And so here's the thing about our atmosphere. It's warm at the surface, and then as you go higher up, it gets colder. And that's because when you mix air and it rises, it decompresses, and when you decompress a gas, its temperature drops. And that means that if something high in the sky is radiating, like up here, it's cold. And it turns out the key thing about infrared radiation that you would have seen if you could see this is that the colder the scene is, the colder the body is that's radiating, the less light you get off of it. And it's quite a strong dependence. It goes as the fourth power of temperature. So if you double the absolute temperature, you get 16 times as much energy coming off of the thing, 16 times as much power. Okay, so this is, this is just a plot. In case you like data, this is if you like pretty pictures. This is if you like data, showing you that it gets colder as you go up. All right, and that means anything up here, if you put the same thing up here, it's going to radiate this kind of feeble radiation. If you put it down here, it's going to radiate lots of radiation. What I was going to show you is a picture of somebody with glasses on, and then you could see that the glasses are really dark and we're not radiating any energy. Maybe you've seen these pictures anyway. Whereas the face would look really bright. Okay, and you can see the same thing if you look at the Earth. These are the Earth's glasses. Okay, so these are clouds way up in the atmosphere, and they are emitting light feebly because they're so cold. They're also reflecting light. This is the visible, what you see in the visible channel. And this is what you would see in the same scene if you looked at it with this camera. So imagining that I'm flying up in space, looking down, and the camera were working, then I'd see that. Okay. So as a consequence, the CO2 is also through the atmosphere. And because if it's very optically thick, if it's opaque, you can't see through it, the light that goes to space has to be coming from up high. Okay? Because anything from down below is never going to make it out. So what you see is the stuff coming from up high, it's cold, and therefore it comes down here. So the point here is that the greenhouse effect depends crucially on having a temperature that decreases and having the absorber where it's cold compared to the surface. So it doesn't work if you do it in a box. All right? So I thought this was kind of stupid, and I thought, oh God, why didn't he come talk to a scientist about this? But more recently, I discovered this. This is an educational resource being used by New South Wales. Angela might know more about who is using it and how. Based on a paper published in a publication called The Physics Teacher, where they proposed pretty much exactly the same experiment that Richard Pearson did as a way of teaching students about the greenhouse effect. So I was pretty appalled when I saw this. Anybody know this journal? Anybody used it? No? Okay, good. Maybe it's really obscure, but somehow the New South Wales government found it. So a bit of horror. When this person did it, and he's from actually very close to where I used to teach, New England and Connecticut, but I never went to that academy. He finds a temperature difference in his bottle of 2 or 3 degrees. So it's a bit like cold fusion. Somehow he's got some effect, but it's not for the reason he's saying. I don't know what is going on. I think he's got a cap on one bottle and it's tight and the other cap is loose, and so the pressure becomes different. And somehow and he also puts it out in the sun. Well, if it were really measuring the greenhouse effect, you wouldn't need to put it in the sun. It'd be better to keep it out of the sun. Anyway, horror. All right. So maybe I should give Pearson a break because there's other people that are ostensibly know what they're doing making the same mistake. So moving from quantum to classical physics, I think now that we've established we can measure the greenhouse effect of CO2, we can also measure how much it's changed over time because of the extra CO2 that we're putting in. We can just use the rules of heat capacity, conservation of energy, We can empirically determine how much of the ocean is absorbing the heat. And we can do this simple problem where we take the heat capacity and divide into it the heat added and come up with a temperature change. And we come up with a temperature rate of change of about 1/5 of a degree per decade. It's not very complicated. And so here's the other plot that we all would like to show. This is temperature since 1880. And you may know that in the last couple of years, we've broken the global average temperature record 2014 broke it a little bit, and that's 2015. 2016 is going to be up there. It's not on the plot yet because the year's still going. And 2017 will probably be down, so don't expect it to break another record after this year. And if you put on there that slope that I just calculated, it kind of agrees pretty well. So I wouldn't say there's too much of a mystery about what's going on. But there is a lot of questions about what's going to happen in the future, because what it basically argued is that CO2 acts like an insulating blanket. If you put an insulating blanket on a source of heat, like this baby, the temperature is going to start to increase, but it's not going to increase forever until the baby spontaneously combusts, right? At some point, you have to reach a new equilibrium, because what happens is, as the baby's temperature goes up, heat will find more and more ways out from under the blanket or through the blanket until finally it comes to a new equilibrium where the temperature is higher than it was. And what we need to know is how fast does the heat, how many ways does the heat find to escape as the system's warming up? Because that's what tells you how much it's going to warm up before it comes to this new equilibrium. So we have to understand things called feedbacks. Okay, so as the temperature rises, there are feedbacks which control how rapidly the energy gets out, or the power gets out. And that determines what happens in the future. So one of the plots that people in my business show all the time is this one. And it shows, here's the observational record. This is a slightly old plot, so there's a couple more years now. And then this is the range of futures that are possible if we don't do any mitigation. And this is the range that's possible if we do lots of strong mitigation policies and really bring the CO2 emissions down. So I'll show you now the new version of this figure as of this week. This is the new version of this figure. We only have one realistic scenario now, unfortunately. So I'll just focus on that one. There's still a very large range here of what could happen. Okay? And the reason for that is that these feedbacks are hard to figure out. Okay, so we don't know whether we would be headed for 3 degrees or 7 degrees of warming. Now, it's tempting to look at this and say, this represents the full range of uncertainty. And most people in my business actually do that. I cringe, but they do. But the problem is, it could be that all these are wrong. Okay, it could be that all of our models are wrong. Because they all have a lot of the same assumptions. You know, people talk to each other and at meetings and stuff. And so here's a great example of where all the models were wrong, just from this week. Okay, polls are models. They're models that are fitted to some data where you then make some assumptions about, you know, how many of this group's going to vote, how many of that group's going to vote, and so on. And there were a whole bunch of models, and they were all up here, and the truth ended up being down there. So that's kind of a wake-up call for modelers. Don't assume that uncertainty is going to be within the range of the models that you got, because it may not. But anyway, we want to understand, first of all, what controls this spread, and second of all, could things be outside of this? Could there be something that we're missing? Now, one thing that we have that the pollsters don't have, and the economists don't have either, which I think makes us a lot less susceptible to that kind of disaster, is that the laws, we're only studying a physical system, it doesn't have people in it, so the laws should be the same over all time. And so if we understand how the system works in one period of time, we should be able to apply that to some other period. And so we can look back at past climate changes, and we can graph on one axis the what we call the radiative forcing, which is the size of that chunk of radiation, the greenhouse effect that we saw, and then the temperature change as best as we can estimate. And these things are hard to estimate, but if you do that for a lot, these are different time periods, last glacial maximum, early Pliocene, PETM is about 53 million years ago, Cretaceous was a lot longer, 200 million years ago, and so on. It kind of, and the yellow shading here shows the models, which were used to generate the previous graph. So it actually kind of supports the models. It supports that there's not something down here or out there, but there's a lot of spread. And the culprit in being able to do a better job with our models is really down to these clouds. So if you think back to the last global image I showed, the red one and the white one, it was showing that clouds reflect sunlight to space, but they also exert a lot of the greenhouse effect themselves. And they have a huge range of sizes. They can be tiny, different altitudes. They behave in really complicated ways. Sometimes they're organized into cyclones. They organize into these quasi-steady convergence zones. There's a nice big, I think that was Yazi, I'm not sure. Yazi's in here somewhere. So it's very hard to deal with this in a model because when we solve the global circulation, we have to do it with boxes that are maybe that size if we're lucky, or maybe that size if we're not so lucky. So in a bad model, Canberra and Sydney might even be in the same grid box. In a good model, there'll be a few grid boxes. But we're not able to resolve all this stuff. So we have to come up with basically mini models that go inside the big model. The mini model predicts what's the net result because of all the stuff you can't actually resolve that's going on in that box. Okay, and so actually though, I think we have an observation that shows that we're not doing so bad. This is a very important paper that came out this year, and they looked at the trends in clouds since 1979 from 2 different satellite data sets, and then this is from those models. And what you can see is that the red is showing where there's a decrease in cloud cover, a blue is an increase. So this dipole here is basically a lifting of the clouds in the upper part of the atmosphere. And then this red here and blue here is an outward shift of the cloud distribution. And decreases, strong decreases here. And that's pretty close to what this is what the model's predicting. This is a more recent observed product where they've tried to correct for weird artifacts in the data. And it's noisy, but it looks, I think, impressively like that. This is an older product which has some character of this, but looks fairly different. So I'd be tempted from this to say, well, this is a better observational product than that one, and the model's doing pretty well. It would be nice if both of the observational products looked more similar. But I think this is but you can even see this dipole up here. It's just a little harder to see. So, and that's important because when the clouds get higher, their greenhouse effect increases. So that's part of the positive feedback that we think we're going to get from clouds. So we actually we're not completely operating in the wilderness. We have some evidence that these models are sort of doing the right thing in spite of all that complexity. But we also have things, so it'd be nice to just pat ourselves on the back and say, we've done this problem, we know what's going to happen, and great, let's go have a champagne. But unfortunately, there's some things going on that we don't understand yet, and I think it's really important for us to attack these. So I like to talk about mysteries and enigmas, and the enigmas are the interesting things, because those are the things that we see robustly in the observed record that seem to contradict what our understanding tells us ought to have happened. I'm going to give you a couple of examples of those. But apart from that, we also know that if we look at our models today, what they do in today's climate and compare them with the real world, we see lots of things that are wrong. They rain at the wrong time of day. They drizzle all the time. They don't form the right kinds of blobs of clouds like we saw in that image. And they give that spread of answers for future warming. We don't know which one's right, but we know that they can't all be right because they're all giving us different answers. So something's wrong in some of the models. And they make this thing called the equatorial cold tongue that stretches too far across, which is actually important for Australia because it means that regional simulations gets disturbed by that error. So it'd be nice to try to solve some of these. And the research program that I'm leading now in our CCRC Climate Center is to try to look at whether we can explain some of these enigmas and maybe resolve some of these model errors by looking at how cloud processes are represented in models. So one enigma that's been around for a few years now is this idea that the tropics are expanding a lot faster than models say. So this is a paper from 2009 where they looked at 2 different ways of measuring the width. So the meteorological tropics have an edge, which is based on the overturning circulation in the atmosphere, and it's based on where the clouds are. There's a change from a dry zone to a wet zone. And the observation suggests that this has been growing since the late 1970s by something like 1 or 2 degrees per decade. And so there's the observations. There's a fair bit of uncertainty on it. And here's a bunch of models. So this is from this paper from 2009, showing that they looked at a whole bunch of climate models, and none of them reproduced this. So this became a focus topic for the community. What's going on here? Is this real? And why don't the models get it? And a postdoc in my group, Damianos Mansis, has been looking at this in newer models, and one in particular from NCAR. And basically what he's done is he's gone back and looked at very long simulations of the climate without any forcing, without volcanoes, CO2, or anything else, just to see how much variability do you get in the natural system. And then he picks out where in 150 years of record you see the biggest tropical expansion simulated by the model. And actually he finds quite a few models that are comparable to the data. So the data are here, 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 and the black dots, forget the other colored dots, the black dots are a bunch of models. So oddly enough, even though this result was published and got a lot of attention, some of this is because the newer models are better, but some of it is because it looks like we just happen to have had a natural fluctuation over the last 20, 30 years that made the tropics get bigger that's not going to last. And I think the clincher in showing that is this is the change in ocean surface temperature over the observed trend where the tropics got bigger. And this is the change in outgoing radiation to space. And then this is the pattern that you get in those models. If you go to each model and you find a time period where its tropics got wider, it turns out that it's happening for a very similar reason in the models as what we've recently seen in the observations. So there's some kind of natural mode. And there's a lot of work on this mode. It's basically something that's called the Pacific Decadal Oscillation. And, but nobody realized it was, well, people recently have suggested that it might be affecting tropical width. But I think what we've kind of done is, in my mind, we've put this enigma to rest. So that's a bit disappointing. I thought we had an enigma that we could try to explain, but it actually looks like it's just because, coincidentally, something unusual happened in the last 20 years. And we have several lines of evidence that are consistent that say that that's what happened. So another enigma that's been around, which I don't think has been solved, is that in past climate changes, the high latitudes seem to change temperature much more than the low latitudes, at least 3 times as much. So here's just one paper that came out last week, I think, by Tim Herbert et al. And this red curve is, geo people like to plot time going backwards. Sorry about that. So this is now, and this is 7 million years ago. Sorry, the scale's off of here. So going back in time, they see the tropics warming up by about 2 degrees, and they see the high latitudes warming up by about 8 degrees, 8 or 9 degrees. So that's at least a 3-to-1 ratio. And when you run models, you don't get that big of a ratio. And we see this not only over the last 7 million years, but also if you go back 50 million years, there's indications of the same thing. You have crocodile fossils from Ellesmere Island, which was in the Arctic Circle, at a time when the world was very warm, but it's hard to explain how it could have been that warm to have a crocodile near the North Pole. And we haven't sorted this out yet, I don't think. So that's one of the problems. I don't have any results to show. I haven't solved this one, but this is one problem that we want to look at. And I think it needs to be solved before we can completely trust what we're saying about future climate. Another enigma that we are working on in my group is the mid-Holocene Saharan greening problem. So if you go back, this is a map that I found somewhere, and I'm sorry, I forgot to put the attribution on. It's very terrible. All you students always put an attribution on your slides. This is what things look like more than 8,000 years ago. But then in the middle Holocene, settlements moved away from the Nile out through the Sahara. Those green dots, red dots are settlements. And then in the more recent part of the Holocene, they've started moving back again to where they are today. And other estimates, other evidence from plants shows that it was raining a lot in the Sahara 6,000 years ago. And the reason for this is almost certainly because of the precession of the equinoxes of Earth's orbit. At these times, the Earth was closer to the sun during the northern hemisphere summer and was farther away compared to today. Today, we become very close to the sun during the summer here, whereas at this time it was more toward the northern hemisphere summer. So that means that there's a lot of sun hitting the Sahara during the summer, which heats it and hot air can rise, and you can generate circulations that would bring rain into the area. But the problem is that when we try to simulate this with models, they never seem to do this, or they do it a little, but they don't do it enough. So this has been a problem that's been lurking in the paleoclimate community now for at least 10 or 15 years, and hasn't been solved. So this is, so people in my group are looking at different explanations for this. And one of the tools that we're using is running high-resolution simulations of regional climate. So this is a simulation, this is the Gulf of Carpentaria here, and this is a phenomenon called the North Atlantic or North Australian cloud line, which regularly sweeps across. It's a density current created by the land-sea contrast here. It sweeps across and triggers clouds. And postdoc Ryan Avi, who's sitting in the back, made this nice movie. I don't know how he did it. You can ask him. But we're trying to use this phenomenon to test ideas about when clouds grow and how much they grow and in what conditions do they not grow. We also have this great new satellite that was just launched called Himawari 8. And this is imagery from this satellite. And what I want to have you look at is this wavefront. There's a storm that occurs here. And then it actually sends out a gravity wave, a buoyancy wave, high-velocity buoyancy wave. I've never seen this in satellite imagery before. The unique thing about this satellite is it takes an image every 10 minutes at decent resolution and allows you to actually see this stuff happening. So we're hoping that we can explain some of this by bringing models and data together. Now here's another interesting simulation. This is a super high resolution one. I didn't do this. This was done by a fellow in New York. He calls it Giga-LES, large eddy simulation. It's 2,000 by 2,000 numerical grid, and he's simulating over a patch of ocean what would happen if you started it with no clouds and then waited. The sun is heating it. Clouds start to form. Eventually they start raining, and they start organizing into bigger and bigger structures. So this is an interesting kind of self-organization that we see repeatedly in simulations of clouds, and we don't really understand it. And then finally you see these gust fronts that come out when rain develops, and that can trigger more clouds. And all of this has to be taken into account when we try to predict what happens in a changing climate with clouds. So the last thing I'm going to talk about, we're using all these models. One of the most important ways that you can use a model like this is not a simulation of any real place, but it's a test bed. You can use simulations like this to test ideas by asking yourself whether your idea of how a cloud works is consistent with this. And we're doing that. So there are some very simple ideas about how clouds work that you find buried in all climate models. They tend to assume that these clouds reach up like elevators, like lifts, and the air goes in the bottom and it comes out the top, and they have kind of straight sides, and there's lots of shear at the edges of the cloud, kind of like a plume, like you had a hose and you let it go up in the air. But when you look carefully at clouds, you find that they don't look like that. They actually have bubbles that go up through them, thermals. And you can see there's multiple ones going up in this cloud system here. Okay, and they kind of have a you can see that they have a circulation like this as they go up. It's actually quite different from what's in that conceptual model. And so here's a rather old simulation that we've done in 2 dimensions where we can isolate one of these thermals. And the red color there is showing you the vorticity of the field. So there's a big updraft in the middle, there's vorticity here, and the whole thing is moving up. And it's quite a different structure from what's assumed in these simplistic models. And it's rather close to something in fluids dynamics called Hill's vortex. Not exactly, but rather close. And it's very different from what you get with a solid object moving through a fluid, which is, well, it's actually not usually used in cloud models, but in some. So these things are very interesting. They can move through fluid kind of effortlessly. And I was going to bring a device for making smoke rings to show you, but I didn't. Sorry about that. And this thing didn't work, so I completely struck out. But the dynamics of these things is really quite different from the dynamics that's inherent in those simple models. And so we've done simulations where we look at the dynamics, the force balances on cloud elements that move up. And we've discovered that the force balance is quite different from what people would have assumed. And in particular, what's interesting is that even though these things are vigorously mixing as they go up, they're not protected. They mix with their environment. But even though they mix, they don't lose any momentum as they rise, which is something that people didn't expect. And we think the reason for that is shown by a simple diagram here. They flow up in this sort of way, and they exchange mass with their surroundings, but they don't lose any momentum because there's no shear right at the edge of the thermal. There's actually a circulation with a maximum in the middle that gradually tapers to zero. So you might say, well, who cares about all this? It can make a difference when you put it into a simple model of a cloud, such as what's used in a GCM. And we already knew that there was a problem with the way we're representing clouds and models because in most models, which have a plume, you have to tell how much mixing there is. And you have to give them actually an extremely small number. But when you do explicit simulations, you find that the mixing rates are very high. But if you put such a high mixing rate into your simple plume model, you never get any clouds. So people just change it. Okay, anytime you're changing something the wrong number in order to get the right answer, you know you're missing something. So we think that what's being missed is potentially aspects of the dynamics of the clouds. And I've only shown you one example, but we're also looking at some of those expanding cold pools that come out of rain systems and the role that they play in triggering clouds. And I'm going to skip over this slide because I'm already at my 45 minutes and just go to the conclusions. So anyway, just to sum up that last bit, I'm hoping that those kinds of studies, together with the regional simulations and all the other things, and the data that we have, we will make some progress on figuring out some of these enigmas. So the conclusions, before I take some questions, we know climate is sensitive to CO2, and we know why. This is not in doubt. We have measurements. And I think it's important for people to understand this, particularly people in physics and in climate and teaching physics, to understand how this process works. But at the same time, there's things that we don't know. And I think it's important that we explain these things. I think until we can explain these enigmas in the past record, and until we can account, at least approximately, for these systematic model errors, we can never be completely confident that our predictions are right. Of course, if our predictions of global warming are wrong, they may be too small, as much as they may be too big. So it's not exactly cause for comfort, but it'd be nice if we could sort it out. And I think that the treatment of clouds and turbulence in the atmosphere is a really important thing that is complicated and we don't know how to do yet. And there's a lot of interesting work going on. I think that the way we simplify this in climate models is we know it's wrong. It needs to be changed. And it's an exciting time to be doing this because we have new satellite observations like the one I showed and bigger computers, and high-resolution modeling is really becoming widely adopted, and it's being used to do more interesting things than what it used to be used to do, to really try to learn about the physics of the problem. And then the last point here is that the World Climate Research Program has launched some new grand challenges, and there's one that I'm involved with, which is meant to sort of coordinate the world's efforts and motivate people to tackle these problems. So I'll stop there and take any questions.